We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
I feel the liftoff. The clock has started. Roger. Godspeed, John Glenn.
Roger, 0G, and I feel fine.
This is a new and strange environment at first. Just suddenly finding yourself in orbit.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11. Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 19 of the Space Rocket History Podcast. And now, Little Joe, Mercury's test vehicle. In 1958, Max Faget became one of the 35 engineers who formed the Space Task Group. This group created the Mercury spacecraft. Faget based his designs on the aerodynamic work of Harvey Allen from the mid-1950s. The Mercury program was to rely on two boosters, the Redstone and the Atlas. Unfortunately, both boosters had some reliability issues that could lead to a catastrophic explosion. This put the Mercury 7 astronauts under a considerable amount of danger. In order to provide a means of saving the astronaut in case of a catastrophic booster failure, Max Faget and other engineers from the Space Task Group designed an escape tower for the Mercury capsule. It was officially known as the Aerial Capsule Emergency Separation Device. It consisted of a rocket and a frame attached to the top of the crew capsule. The idea was if the booster failed, the escape tower would pull the capsule to safety. Now, of course, a system such as this would require multiple tests before it could be considered operational. In addition to testing the escape tower, capsule aerodynamics under actual re-entry conditions and the recovery system needed to be tested as well. The cost of the Atlas booster was about $2.5 million in 1958, or about $20 million in today's dollars. The Redstone booster cost about $1 million in 1958, or $8 million in today's dollars. The managers of the Mercury program recognized that the numerous early test flights would have to be accomplished by a far less expensive booster system, and they preferred a simple design without any electronic guidance and control systems, and that would use solid fuel and existing proven equipment. In January 1958, Max Faget and Paul Purser had worked out on paper how to cluster 4 of the solid-fuel Sargent rockets that would be capable of boosting a manned nose cone above the stratosphere. The Sargent rockets were in standard use at the Wallops Flight Facility in Virginia, and thus proven equipment. In October 1958, a NASA team prepared new engineering layouts and cost estimates for the mechanical design of the booster structure and a suitable launcher. As the blueprints for the cluster of the 4 rockets began to emerge from their drawing boards, the designer's nickname for the project gradually was adopted. When you look at the top view from the end of the booster, the 4 Sargent rockets resemble gambling dice. It looked like a throw of double deuce on the dice, which in the game of craps is called Little Joe. The appearance on engineering drawings of the 4 large stabilizing fins protruding from its airframe also helped to perpetuate the name Little Joe. Eventually, 4 smaller recruit rockets were added to allow the Little Joe to better simulate the Redstone and Atlas boosters. North American Aviation won the contract to build the Little Joe and began work immediately on its order for 7 booster airframes and 1 mobile launcher. In May 1959, North American delivered the first 2 Little Joes at a cost of $200,000 each, or $1.6 million in today's dollars. This worked out to be about 1/5 the cost of a Redstone booster. The finished Little Joe rocket was 55 feet long and 6.5 feet in diameter. It ran on solid fuel with a max burn time of 37 seconds. It consisted of 4 modified Sargent, called either Castor or Pollux rockets, depending upon modification, and 4 supplemental recruit rockets arranged to fire in various sequences. The takeoff thrust varied greatly, but maximum design thrust was almost 230,000 pounds. This was theoretically enough to lift a spacecraft of about 4,000 pounds on a ballistic path over 100 miles high. The push of these clustered main engines would simulate the takeoff profile in the environment that the manned Atlas would experience. Furthermore, the additional powerful explosive pull of the tractor rocket escape system could be tested under the most severe takeoff conditions imaginable. And now, the Little Joe missions. On August 21, 1959, at Wallops Island, Virginia, the first Little Joe, LJ-1, was sitting on its launcher tilted toward the sea, with a full-size model capsule and escape system on top. Its test mission was to determine how well the escape rocket would function under the most severe dynamic loading conditions anticipated during a Mercury Atlas launching. At 35 minutes before launch, evacuation of the area was proceeding on schedule. Suddenly, half an hour before launch time, there was an explosive flash and roar. Somehow, the escape tower had been activated, leaving the unused booster on the launch pad. No one was injured, but when the smoke cleared, it was evident that only the capsule and tower combination had been launched on a trajectory similar to an off-the-pad abort. The booster and adapter clamp ring remained intact on the launcher. Near apogee at about 2,000 feet, the clamping ring that held the tower to the capsule released, and the little pyro rockets for jettisoning the tower fired. The accident report on LJ-1 issued on September 18th blamed the premature firing of the escape rocket on an electrical problem. This first trial of the brand new Little Joe test booster apparently had been too ambitious. Fortunately, the momentum of the Little Joe test series was not disturbed by the debacle. On October 4, 1959, the same booster that had been left by the capsule and escape rocket in August was finally fired, this time with an uninstrumented boilerplate model fitted with an inert escape rocket system. After the fiasco of LJ-1, the more modest purpose of this test, which later became known as Little Joe 6, was to prove the reliability of the whole booster propulsion cluster. All 4 Sargent motors plus 4 smaller recruit motors were set to fire in sequence. Little Joe 6 blasted up to a peak altitude of nearly 40 miles, achieving a maximum speed over 3,000 miles per hour. After 2.5 minutes of flight, it was intentionally destroyed in order to test the destruct system. Impact was over 70 miles from Wallops Island. All went well with this flight. Satisfied that Little Joe had proved itself as a booster, the supervisory team of NASA engineers prepared for a new effort to check the correct operation of the abort escape system at maximum loading conditions. The region called Max Q, for maximum dynamic pressure, is the portion of the flight path at which relative speed between the vehicle and the atmosphere produces the greatest air resistance on the vehicle. Many variables were involved, but roughly both Little Joe and the Mercury Atlas were expected to experience dynamic pressures of almost 1,000 pounds per square inch at an approximate altitude of 6 miles after 1 minute of flight. For the second attempt at the primary mission, Little Joe 1A needed to propel another dummy capsule and an escape tower to the Max Q region. Both drogue and main parachute behavior were to be carefully studied on this flight as well. On November 4, 1959, Little Joe 1A was successfully launched. The flight looked straight and true until the rocket was out of sight, but the test engineers in the control center observed that the escape motor did not fire until 10 seconds after the point of maximum dynamic pressure. The parachute and recovery operations performed well enough to fulfill secondary and tertiary objectives, but precisely why the escape system was too slow was not fully understood. Later analysis showed only that the delayed ignition of the escape rocket caused the separation of capsule from booster at a pressure of only 1/10 of max Q. Because the next scheduled launch of Little Joe booster was already committed to a test for certain aeromedical objectives and was now in the late stage of preparation, the primary aerodynamic test of the escape system was postponed until January, when a third try, to be called Little Joe 1B, could be made. Back in May 1959, the Space Task Group had begun planning with the Air Force School of Aviation Medicine to include some biological packages in Little Joe flights. The booster designated number 5 was reserved specifically to qualify all systems in the McDonnell capsule carrying a chimpanzee occupant and escaping from a simulated Atlas explosion at the point of max Q. The School of Aviation Medicine had made ready a biological package for its primate passenger, which was a small rhesus monkey named Sam. He was named after his alma mater, School of Aviation Medicine, SAM. In addition to Sam's special capsule for rocket flight, the military physicians now prepared barley seeds, rat nerve cells, neurospora, tissue cultures, and insect packets to measure the effects of primary radiation, changes in appearance and capacity for reproduction, and ova and larvae responses to the space environment. Little Joe 2 promised to be a spectacular flight if everything went as planned. The engineers would be able to see how the capsule escape system would function under conditions of high Mach number and low dynamic pressure. More important, technically, they could measure the motions, aerodynamic loads, and aerodynamic heating experience of the capsule entering from the intermediate height of about 70 miles. The Air Force medical specialists might also learn about other things, but their chief interest was to see how well Sam himself would withstand weightlessness during the trip. This was also the chief interest of Alan B. Shepard and Virgil I. Grissom, who came to see this launch. On December 4, 1959, just before noon, the third Little Joe, LJ-2, ripped through the air under full power and burned out at an altitude of 100,000 feet. The tower and the capsule separated as planned, and the escape rocket gave an additional boost, throwing the capsule into a coasting trajectory that reached its zenith just before 280,000 feet, or 53 miles. This peak height was about 100,000 feet lower than expected because of a serious windage error. So Sam experienced only 3 minutes of weightlessness instead of 4. He survived the mild re-entry and the not-so-mild impact and 6 hours of confinement before he was recovered by a destroyer and liberated from his inner capsule. All preliminary indications reflected a highly successful flight. For the first time, Little Joe had achieved full success on all 3 orders of his program test objectives. Congratulatory letters sped around the circuit among those responsible. It was a satisfying way to close out the year. But the Space Task Group engineers knew that this full performance test of the Little Joe was not the most crucial case for man rating the Mercury escape system. They still had to prove that at max Q, where everything conspired to produce failure, the escape system could be relied upon to save the life of any man who ventured into this region aboard an Atlas. This brings us to Little Joe 1B and another biological test flight. On January 21, 1960, with John Glenn and Alan Shepard in attendance, the fourth launching of the Little Joe occurred. The escape system performed as planned at the point of max Q. Propelled by two Sargent main motors, Little Joe 1B blasted up to the nominal altitude of slightly less than 9 miles and attained a maximum velocity slightly over 2,000 miles per hour. Then the escape rocket ignited for an additional 250 feet in 1 second to rescue the Mercury replica from a simulated booster failure at that point. Over a range 11.5 miles out to sea, Miss Sam, another Reese's monkey, in her biopack prepared by the medical technicians from the School of Aviation Medicine, not only survived the severe G-loads, but also performed well at her business of watching for the light and pulling the lever. After 8.5 minutes of flight, during which the sequence systems and capsule landing systems worked perfectly, Miss Sam touched down. She was recovered almost immediately by a Marine helicopter and was returned in excellent condition to Wallops Station within 45 minutes after liftoff. For half a minute after the escape rocket fired, the little rhesus monkey had been badly shaken up and did not respond to stimuli, but otherwise Miss Sam acted the role of the perfectly trained primate through the flight. Evidence of Miss Sam's oscillating motion of her eyes after escape rocket firing and after impact on the water did cause concern, for it suggested that an astronaut's effectiveness as a backup to the parachute system might be impaired. The internal noise level proved to be higher than expected, likewise causing some other worries over the provisions for communications and pilot comfort. But this flight proved that a booster explosion might be survivable. The next flight was called Little Joe 5. It was planned for over a year to be the first qualification flight of a real Mercury production capsule to sustain abort conditions at maximum dynamic pressure. Holloman Air Force Base personnel had prepared a medium-sized chimpanzee for this flight in order to determine the effects of a simulated Atlas abort acceleration on a chimp. However, the delay in capsule delivery and a large number of checkout difficulties encountered in late August, especially with the booster capsule clamp rings and pyrotechnics, led to not using the monkey on this flight. On Election Day, November 8, 1960, Little Joe 5 was launched. Unfortunately, it disintegrated 16 seconds after liftoff. At that time, the escape rocket and the tower jettison rocket both prematurely ignited while the booster was still thrusting. Therefore, booster, capsule, and tower stayed mated together throughout their ballistic trajectory until impact shattered them to fragments. Spacecraft and booster flight went 10 miles high and 13 miles out to sea before being mangled on impact 2 minutes later. Salvage operations in the water 72 feet deep recovered 60% of the booster, but only 40% of the capsule. The problem was attributed to the clamp rings. As a result, extensive tests on the clamp ring problems were conducted on rocket sleds at the Naval Ordnance Test Station in California. The next flight was Little Joe 5A. By this time, NASA was down to its last Little Joe test booster on hand, but they did have one ordered. On Saturday, March 18, 1961, after a 4-hour delay caused by checkout problems, Little Joe 5A launched from Wallops Island at 11 minutes before noon. The takeoff looked good, but 20 seconds later, and 14 seconds too early, the capsule escape rocket again fired without the capsule. At 35 seconds, the normal abort signal released the capsule clamp ring. A single retro rocket, which was installed as an emergency separation device, received a premature firing signal at 43 seconds. The dynamic pressure at this point was 400 pounds per square foot, 10 times as great as the dynamic pressure at apogee, where emergency capsule separation should have taken place. The capsule tumbled immediately upon separating and narrowly missed the booster as it decelerated. The retro pack and the escape tower were inadvertently jettisoned or torn off as the capsule tumbled. Apparently, the centrifugal force of the escape tower removed the antenna canister as well, deploying both the main and the reserve parachutes. The capsule descended on both parachutes, which were only slightly damaged during high Q deployment. Post-flight analysis showed that both LJ-5 and LJ-5A had failed primarily because of structural deformations near the clamp rings that fouled the electromechanical separation systems. The impact bag on Little Joe 5A was deployed at 10,000 feet. The capsule drifted 10 miles on both its parachutes and finally splashed down 18 miles from the launch site, almost twice as far as planned. On top of that, the parachutes fell unreleased over the capsule as it floated in the water, thereby preventing helicopters from recovering it. A Navy salvage ship made the pickup an hour later. The capsule was in fairly good condition with only one shingle damaged from its ordeal, and parachute loads 6 times higher than expected had caused no significant damage to its structure. Little Joe 5 had been a spectacular failure. The primary objective of qualifying a Mercury capsule during a max Q abort had to be rescheduled, utilizing the last Little Joe booster. The Little Joe 5 capsule was cleaned up, repaired where necessary, and furnished with another set of sensors, instrumentation, and telemetry for the reflight coming up. There was no time for more contingency planning if the U.S. hoped to orbit a man before the end of 1961. The escape system had to be proved before the first manned Mercury Redstone mission. Which brings us to the final flight of the series, Little Joe 5B. Little Joe 5B was fitted with the Little Joe 5A capsule and made ready for a repeat of the Little Joe 5 and Little Joe 5A missions in hopes that the third time would be a charm. In addition to the redesigned clamp ring and limit switches, more instrumentation and even more careful checkout procedures were implemented to ensure that the abort would occur at the right time. This mission called for a steep trajectory up to about 45,000 feet before tower separation and drogue chute deployment. The max Q pressure of about 990 pounds per square foot was desired to match the worst of the Atlas abort conditions. On April 28, 1961, Little Joe 5B launched. Technical observers cringed when they saw immediately that one of the booster's Sergeant rocket motors failed to ignite for 5 seconds after liftoff. This resulted in a much lower trajectory than planned, giving it a maximum altitude of only 14,600 feet. But the dynamic pressure, instead of 990 pounds per square feet, was about twice that amount, 1,920 pounds. The abort was initiated after 33 seconds after launch as intended, and all events followed the abort occurred as they should have. Recovery by the helicopter was quick and clean, even though the low-flying capsule impacted 2 miles further downrange after skidding through the atmosphere rather than vaulting through it. Little Joe 5B accomplished the primary objectives for the series. Specifically, it proved the escape system under max Q, and it demonstrated the structural integrity of the Mercury capsule. Furthermore, it worked under significantly more severe conditions than those expected to be encountered during an abort from an Atlas booster during a Mercury orbital launch. The changes in circuitry and redesign of the clamp limit switch eliminated the problems of premature ignition of the escape rocket motor. Little Joe had cleared the way for Alan Shepard's suborbital flight on a Mercury Redstone just 1 week later, on May 5th, 1961. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.